Right, okay, so Samo is ready. This is him.
Yeah.
This handsome.
Hi, I'm Samo.
So, you want to introduce yourself? Because I have like a list of things. I think it's better if you tell them, because I've been speaking.
I can introduce, yeah.
Yes, please.
Yeah, so I'm a scientist, so it's going to be a bit different presentation from maybe what you're used to. So if you can't follow, maybe stop me and ask for questions. I work at the Zurich University of Applied Research. I'm a chemist, but mostly I work on coffee science. So one of the topics that I work recently is about coffee degassing. This research has been done together with SCA research as well. So we actually don't have so much time, so let's go quickly through this. I'm going to talk about coffee degassing, so explain you what this is, where does this phenomenon come from, how can we measure it, and what is the impact on our coffee and our brew. So first, what is the role of CO2 in coffee? Where does it come from? So, you know, we have green beans, we roast them, and the roasting exhaust already contains a lot of CO2. It also contains a lot of water and VOCs, you know, this nice fresh roasted coffee aroma that goes out through the exhaust. And then in the roasted bean, quite a significant amount of these gases remain trapped after roasting. So after roasting, this gas is trapped in and it's slowly released from the bean. If we grind the bean, we speed up this release very much, so about 10 times. So because this gas is released pretty fast in the ground beans, the ground coffee, so it has an impact on like capsules, but also the roasted beans, if we store them for a long time, because of this slow but quite significant degassing, it has an impact on our packaging. And in the end, it also impacts our extraction. So we have the whole chain from going from green bean to our cup of coffee. This CO2 is always somewhere behind, messing up something or helping us doing something, but probably it's like an underrated molecule in the coffee, because everybody's talking about aroma, the acids, the polyphenols, you know, the antioxidants, melanoidins, but rarely somebody's talking about the CO2 in coffee. So we did research on this to kind of to really go on a basic scientific level first, and then try to apply this research on some practical examples. So first I'm going to talk about where does the CO2 come from. So it was already today in the morning, those who have been at the first lecture here, there was some talk about this. So CO2 comes from two main sources of the reactions that occur during coffee roasting. That's Strecker degradation. It's a type of a Maillard reaction where CO2 is formed. This is mostly happening during the first crack at this stage of the coffee roasting. And pyrolysis, that's this reaction happens at the later stage during the second crack, if we roast that long. So we have first Strecker degradation at the early stage, and then pyrolysis, it's at the later stage of roastings. So this one produces quite some CO2, and the pyrolysis produces really a lot of CO2. So the bean doesn't undergo only the chemical transformations when it's roasted, but also its physical structure changes a lot. So one of the ways how we can see the bean structure on the inside really is with micro X-ray computer tomography. This is kind of the same device as used for medical purposes, just the size scale is smaller and the resolution is much better, so we can see the inside of the bean, and it looks something like that. So this here is a reconstructed 3D model of a coffee bean, which was cut in half in the software. So you can see the inside bean has a very porous structure with a lot of pores. We can see the silver skin here. Here there's a crack, which is happened during the first crack, during roasting. And on the bottom there are slices, so the images of the slices. This thin first slice here. So we have on the left green coffee. We have a very light roast, so it would be immediately after the first crack, a medium roast, and a dark roast. So what you can see here is that the green coffee has a very dense structure. There's no pores. It's like filled with the nutrients in the green bean, the cellulose. And at the first crack, the structure of the coffee gets really porous. These pores are basically plant cells which are inflated because of the forces that are inside the bean during the first crack, and then not much happens on this level from light roast to dark roast. But of course we have all this connective material, all these cell walls which remain, which are the structure of the roasted coffee bean. Probably we can imagine that the structure of those changes from light to dark roast, but on this scale we don't see it. This is on a molecular level. Maybe it changes. Probably it does, because we see some effects. So if we can look a bit deeper into this pore structure, this is an electron microscope image, so it has a better resolution than even the X-ray or with the microscope imaging. We see one of those, so what used to be a cell, biological cell, now it's an empty cavity, and we see cell wall, which is a connecting material. And I would like to talk here about where the CO2, which was formed during roasting, is trapped in. So there's two basic possibilities how it's trapped. So first, we can say, okay, it's trapped as gas in these pores. So these pores, they're some empty volume, which are filled with gas, and we can say, okay, CO2 is trapped in here. But there's also other ways of trapping gas in the material. So it's more physical-chemical sorption on the surface, can be sorbed on the surface, or it can be absorbed in this cell wall material, because we cannot look at this material more in detail, but there have been studies done, and it's shown that this material also has very tiny pores, and these pores are able to store a lot of gas in. So we have macropores, which are the big pores, and then there's the small pores that are in here. And we can have the CO2 trapped there, and because of different mechanisms of trapping, there's also two different mechanisms of release. So release from this macropores would be what we can imagine easier would be, it's called hydrodynamic flow. It's basically, gas is there under pressure, and because of the pressure, it's slowly released through some cracks out from the bean, from the inside of the bean outside, right? The other, so sorbed CO2, so either sorbed on the surface or inside this material, that's a bit different. It doesn't work as we are used to in this our macro world. It works differently on a molecular level. The CO2 diffuses through the material. So because the molecules, they move very fast around, there's always a likelihood that it will find a hole somewhere going out to the outside. And this is called diffusion. And it's not hydrodynamic flow is a physical process, and diffusion is more a physical-chemical process. So what does this mean? This means that if we have outside pressure of air, which has very little CO2, the hydrodynamic flow, the outside pressure of air will be able to block this flow, because it's like a physical barrier. If we speak about diffusion, the molecules don't feel the pressure like on a macroscopic level. They live in their molecular level, and they don't care if there's a high pressure outside. The CO2 will go from the high concentration of CO2 towards the low concentration of CO2, regardless what is outside. So if you have a high pressure outside but no CO2 outside, the CO2 will still go from inside of the bean towards the outside. So this is the driving force of the diffusion. It's a difference in concentration of a certain molecule. So I mentioned that the degassing is slow from a whole bean, but very fast from ground coffee. So why is this? First, if we look at the hydrodynamic flows of this CO2 trapped as gas inside of the bean, that's easy to explain. So we have our bean structure. You saw it. It looks like a brain or a sponge. If we grind coffee, we destroy these pores. Most of them we damage. Some maybe stay intact. Some get cracked. And this CO2, which is there, just goes out very easily and very fast. On the other hand, the diffusion, it's a bit different. After grinding, we speed it up, but not because of the fact that we destroyed the pores, but because we increased the specific surface area of the material. So what does it mean? This means that, if I said the molecule is wandering around inside the bean because it's small and fast, and then if the surface area is larger, then it just becomes more likely that it will sometime just go away. So we speed up the process by having a larger surface area. So the process of diffusion is just faster. So keep in mind these two mechanisms, they're very different in nature, and right now, I would say let's say we don't know which mechanism is dominant in the degassing, but later when we see results, it will be quite clear what is happening. Just a few words on how we can measure this process. So we have, basically we have a solid material that emits gas. So during during storage, with time, it slowly emits gas. So there's two methods that are practical, which are reliable and robust, that produce reproducible results. So one is to measure the pressure increase during degassing. So we have such glass containers. On these glass containers, there are temperature sensors and very precise pressure sensors. We put here a sample of coffee. And for example, here we have a 2-liter glass vessel. We put in 200 grams of ground coffee. After degassing, we build up approximately 100 to 150 millibars of overpressure. And if we assume that the CO2 is approximated by the gas equation, so a bit of basic high school physics, we can calculate from the pressure volume we know. We can calculate, so we know that this is a gas constant. We measure the temperature, so we can measure the amount of CO2. So from the pressure increase, we can then go back to the amount of CO2 that was released from the coffee. Another method which we developed in our laboratory is a gravimetric method. So what is gravimetry? Gravimetry is an analytical way of measuring an chemical analyte by weighing the sample. So any kind of measuring chemicals by weighing, it's called gravimetry. And basically what we do, we measure very precisely the weight of a coffee sample. So we put it in a VSD basket in the sampling container in our special modified high precision balance. And this balance is very stable with time. And because it's so stable and so precise, we can measure the loss of weight of the coffee sample because it's losing gas. So the precision of this balance is about 0.001%. So it's it has to measure in a period of a few months. It has to measure the sample with precision of 0.1 milligram. So it has to be highly precise. But the good thing is the coffee has quite a lot of gas absorbed inside after roasting, so the loss of mass is quite significant. So how do degassing data look like? Just to imagine how such measurements look like. So here we had freshly roasted and immediately after roasting ground coffee, ground to an espresso grind size. It was an Arabica coffee. We measured the degassing So we roasted coffees to various roasting degrees, from very light, that would be like immediately after the first crack, or still during first crack, to very dark roasted degrees. So probably those that you wouldn't want to drink, but we still were interested what is happening if you roast very dark. Here you see it's the degassing time in hours, so it's about one week here, a bit less. And we're talking about specific mass loss because we measured with this gravimetric method. I'm saying here milligrams per gram. So what does this mean? This means that a specific per gram of coffee, this coffee lost around 2 to 3 milligrams of mass. So this would be 0.2 to 0.3% of its mass. We see here an initial very fast degassing immediately after grinding, so a matter of a few hours, we lost more than half to 3/4 of the gas, and then subsequently a slow release. And if we take a look at different grind sizes, different roast degrees, sorry, we see that if we go from a light roast towards a medium roast, we increase the amount of gas released, but if we go from a medium roast towards a very dark roast, we don't see any more increase. So how can we explain this? So our idea is that probably during roasting, towards a medium roast degree, a certain amount of CO2 is formed, and if we roast darker, we form more, but we also lose more during roasting because the coffee structure gets more and more porous, it expands more and more, and so we're losing more already during roasting. So more we produce during roasting, but still more we lose, so we don't get much increase overall in the ground coffee. We also measured, of course, the whole beans. This was a much slower process. Here it was measured up to 20 days, and it still wasn't finished after 20 days of degassing. And we roasted in three roast levels. So we had a dark roast, which would be like a regular espresso roast, a medium roast, which would be more like a specialty espresso roast, and a light roast, which would be a filter roast. And we roasted in 3 speeds, from a fast to a slow. So fast would be around 6 minutes, medium would be 9 minutes, and slow would be around 12 minutes. So what we can see here is that for the dark roast, we have quite an impact on the roasting speed. So roasting fast produces much more trapped CO2 in whole beans. Roasting slow produces less CO2 trapped in whole beans. So this indicates that when we roast slow, we produce more porous beans, and if we roast fast, we produce more dense structure of the beans, which is capable to trap more of the CO2 in still after the roasting. Also here, it's not very well seen, but we're talking about 10 milligrams per gram of CO2 lost during degassing. So this means that about 1% of the coffee beans mass was as gas. So this is quite significant. So if we have a kilo of beans, we leave them standing for 1 month, then suddenly we have 990 grams of beans left. The 10 grams difference was lost as CO2 out from the beans. We saw a similar effect for medium roasted coffee. But there was not really an impact on the roasting speed on the light roasted coffee. And you can also clearly see here that the roast degree has a much higher impact on the amount of CO2 released than the roasting speed. But nevertheless, we still should consider roasting speed as an important factor of how much CO2 is released from beans after roasting. So let's now try to compare the whole beans and the ground coffee in terms of degassing. So I presented the data here now in a different way. So before I was speaking about the mass loss from the beans, so how much CO2 went out. Now I'm presenting how much CO2 remains still in the coffee. So if we go to a long time, this one would go eventually to 0. So that's the amount we have at the start in the beans, in the whole beans. So it's about 10 milligrams per gram, or 1% of the mass. We can assume that from when we stopped roasting to that I started the first measurement in 1 hour, we already lost some. So because the degassing is the fastest immediately after roasting. And okay, then let's first compare the whole beans to the ground and then break down where the losses are. So if we look at the ground beans, we see that the amount is much smaller. Before I said 2 to 3 milligrams per gram. So we have this degassing, which is much faster at the start, and then it slows down, and it goes to 0 at around 150 hours. That's about 5 days in this case. So we have around 2 to 3 milligrams going out from the ground and 10 from the whole. So where's the difference now? The difference is during grinding. So during grinding, in this case, for this specific coffee, of course, for different grind size, different roast levels, we might get different results. But for this specific coffee, we lost three quarters of the trapped CO2 immediately during grinding. You remember before I mentioned it that you should keep in mind these two mechanisms, the very fast hydrodynamic release and the slow diffusion. So now if we have this data, we can now kind of explain what is happening. So we have CO2 trapped in these big pores, which we destroy when we grind, and then it's a very fast process of pressure release, and we lose a lot of CO2 immediately during grinding. And some of it is trapped inside this wall structure still after we ground the coffee, and this is then slowly released out through diffusion. What is also interesting then to do a more practical experiment. So before previous slide, it was whole beans immediately after roasting and ground coffee immediately after roasting. But what happens now if we measure the whole beans, and then we take the same coffee beans and measure them as ground beans, but we measure them fresh. We measure them after 1 week. We measure them after 2 weeks, after 4 weeks, and after 6 weeks. We also measured in 2 roast degrees, the dark roast and a light roast. So we saw here that, of course, this typical drop in the loss during grinding, and then we have, whole beans. We go to 0 here in about 40 days, so 1.5 months, a bit less, and when we have each of the ground. So what we see here is very interesting, is that this loss during grinding is very high when we have fresh coffee, but then it's less and less, and here we come to a very, very interesting phenomenon. So what is happening here, I hope you see because it's quite low. So the whole beans were nearly degassed completely after 4 weeks, but then we ground the coffee and we still got quite a lot of CO2 coming out from the ground coffee. So what does this mean? This means that in the whole bean, there are pockets where the CO2 is trapped quite strongly and doesn't get released from whole beans, and these pockets are open for CO2 to be released only after we grind it. And that's actually very good for us, because it helps us to have coffee that is 1 month old, that's not perfectly fresh, but if we will consider degassing from whole beans, it's practically stopped. But but when we grind them, we can still access some CO2, so that we still have some freshness. Of course, we all know CO2 is important for crema formation, so we want our crema. So that's important that we still keep some in. What is interesting, that if we take a look at dark roast and light roast, here we have approximately half values for everything. So here was a start at 14 for this particular coffee. It was not a dense coffee. It was a very, very low density Guatemalan coffee. So it had 1.5% of gas trapped in its mass after roasting for the dark roast. And if we compare dark and light, we kind of see that everything is approximately halved. And also you see that after 4 weeks, it was for both, it was the turning point where from ground we had a higher release than from the whole beans. How can then we compare different, how do different whole beans compare in degassing? So before we had a Colombian coffee, which was about 10, but actually if we degassed much longer, we saw that it goes up to 12 milligrams per gram in degassing. And I mentioned this Guatemalan, which was very low density and became very porous during roasting. It degassed really fast, and it went up to 14 milligrams per gram degassing. We also measured one other coffee, which was comparable to this one. I actually have data for, these are all washed coffees. I have also data for one natural, but it somehow slipped away. It's not on this plot, and it was similar to those. So there was not really a big difference in washed and natural processed, but there seems to be a difference in how dense the beans are. So very dense beans, they will also then form a more dense roasted bean structure, which will degas slower and maybe less. And low density beans, they will degas really fast. So we already started now discussing a bit about how CO2 impacts our coffee. So what is the impact of CO2? Already at the start I mentioned one of the obvious impacts is packaging, right? Theoretically, the effective internal pressure in the bean can be calculated to 10 bars, but keep in mind this is an effective value because it's chemically sorbed in the surface, so we cannot go with a pressure meter inside and measure 10 bars in the bean. This is if we calculate the volume of the bean and the total CO2 that is sorbed inside. But still, when it's degassing, it can produce significant pressure in packaging. And I don't know if any of you already did an experiment where you packed coffee in a coffee bag without a valve. And believe me, sooner or later, it will explode. So we all know we have to keep the valves there to let the CO2 be released out during storage. What is also nice of that our CO2 is released during storage is if we pack our coffee in the bags under normal atmosphere, we have 20% of oxygen in. So because 20% of oxygen is in the atmosphere, right? So if we have in the bag CO2 coming out from the coffee, this CO2 is pushing out also the oxygen when the coffee bag starts to inflate and opens the valve that is releasing the gas out. So the CO2 will also push oxygen out. And during storage, the coffee in bag, so the CO2 in the bag will produce a partially protective atmosphere. So it will reduce the oxygen level. Depending on how much we pack the bag, it can reduce the oxygen to 10 or even 5% only. So that's a kind of a natural way of making, I would say I call it a partially protective atmosphere in our bag. So it's not really like packing the coffee bags under nitrogen, but it still helps a great deal to prevent oxidation of our coffee during storage. Of course, that's another point, right? Speaking about oxidation, CO2 is one of the causes of the migration of the oil from the inside of the bean structure outside because it's pushing out the oil. And once the oil of the coffee oil is on the surface, it comes to contact with oxygen and it's highly prone to oxidation. So once this happens, you don't want to drink this coffee anymore. And for example, with the previous mentioned Guatemalan coffee, which was very porous, produced a lot of CO2, it also got the oil migrated very fast on the surface of this coffee and was stale very fast because of that. So since we're talking about packaging, I attempted to do a bit of, this is theoretical, these are not measurements. So to see since we now know how much CO2 is potentially released from the coffee, we can then try to estimate what pressure can be built up in packaging. So a red line is the most extreme example. If we have a rigid container that does not change its shape and we completely fill it with coffee, we can get potentially 2, 3, 4, 5 bars of pressure inside with time. Of course, there's a red area here because if we start to increase the pressure, I mentioned before, because of diffusion, the chemical physical processes, the CO2 will at some point stop diffusing from the coffee, and it then will stay like, okay, outside there's so much CO2, the CO2 will feel like, okay, I don't want to go outside from the coffee bean anymore, and it will stay inside the bean. So where this is, right now I can't tell how far we can go, but that's also part of the measurements we maybe do in the future. So if we have a bag with no valve, we see that we can also get quite a bit of increase in pressure, and 2 to 3 bars, that's for sure, as I mentioned before, more than enough that the bag would not withstand and would explode. One question here, if somebody knows why there's a bit of lag from going from here to here. So for the first day, there is no pressure increase in the bag. Any idea? So once we pack the coffee in the bag, if we really don't fill it up completely, so for example, if we have a 250 gram bag and we put in 250 grams of coffee inside, the bag is not completely full, it's not like we're blowing it up completely. And the bag will first unfold and will expand, not really expand like the material, but will unfold, and because it will unfold, there will be a bigger volume in the bag. So we don't see really an increase in pressure for the first day in the bag, but then once there is a certain it takes a certain shape, so when it cannot unfold anymore, then we will start to see the increase in pressure. Luckily, if we have a valve, the valve will then open up after a bit of overpressure in the bag, and then it will release the CO2 out. So another thing that we should keep in mind is safety here. So the amount of CO2 that is released from the coffee during degassing, it's not really problematic if we're not dealing with tons. But there's an unfortunate thing, because the coffee roasting produces the pyrolysis reaction during coffee roasting. The pyrolysis produces carbon monoxide because of a partial oxidation of organic matter in coffee. And carbon monoxide, as you know, it's highly toxic. So there's one report that there's about 7% of carbon monoxide in the gas released from coffee during during grinding. So the gases that are released during grinding, and this is a bit critical, maybe. So it is very toxic. So the limits are 30 ppm for long-term exposure, and short-term exposure 200 ppm of carbon monoxide. What does this mean? How much is this? 30 ppm, 200 ppm, to have like an example. If we say that 8 grams per kilogram of gas is released during grinding, if we grind a freshly roasted coffee, that would be about half a liter of carbon monoxide per kilogram of coffee. That's quite a lot, but luckily the volumes, when we speak about the volume of this room, it's still very little compared to the volume of the room. So if we take a regular a larger residential room, we can say that it has a volume of around 100 cubic meters. So grinding 1 kilogram of coffee would increase the CO concentration in this room to about 5 ppm, which is perfectly fine. That's nothing dangerous yet. Of course, here we assume that we have a completely sealed room with no ventilation or any open window or open doors. But of course, none of our living environments are completely airtight. So there's always some recirculation with the outside. So a typical air exchange rate in residential buildings is around 1 volume per hour. And so this means that if we would grind 1 kilogram of coffee each hour in such a room, we would get to about 2.5 ppm. So this is for like smaller amounts. But of course, if we start talking about industrial amounts of industrial production or very small coffee shop which is not well ventilated, which grinds a lot of coffee, we can certainly reach this 30 ppm limits, but the solution is quite simple. We just need a well ventilated room where we do such things. So when we grind coffee or where coffee is stored, or of course with roasting, it's also if the Ikava roaster where it's going just out, we have to have ventilation. I know a story from a big company where they had a silo where they were curing coffee, so basically degassing before it was packaged. So it was as I don't know if it was as whole beans or ground, but basically there was a silo which is open, and so this guy was a scientist there. He told me that one of the managers went there and he just did this over the silo, and he fainted immediately after one breath of this atmosphere above the silo. So luckily he didn't fall in the silo because he would die. He fell behind, but he was unconscious after one breath. So that's because there was first a lot of CO2, so there was no oxygen. But even more critical is the CO, which is toxic, and basically its effect is such that our blood, after it comes with contact with CO2, cannot take up oxygen anymore. So it can be dangerous when we deal very, very large quantities. So talking about degassing, of course, everybody is also thinking about freshness, because coffee that is completely degassed, it's flat. And the fresh coffee, it always has a lot of gas in, so when we brew it, we see a lot of gas released, right? We can, maybe that's not so, that's a bit too technical, but we can measure degassing, and we can evaluate how fast it's released from the coffee. We can measure also aroma, so those are 3 very volatile aroma compounds which are released very fast from the coffee, and we can evaluate how fast this goes, like a specific time constant for a specific chemical, and we see that CO2 is way lower than the aroma compounds. So methanol, that's by far the most volatile. It's comparable to CO2, but all other aroma are way less volatile than CO2. So it takes them much longer before they are released. So this is kind of good for us, because this means that we get rid of this excess CO2, which is not very good for us, because we cannot make, for example, espresso with a very fresh roasted coffee, but the aroma is we're losing it slower. So we have to wait for the right time where we lost enough CO2 to make our good coffee brew, but luckily the aroma is lost slower, so we still keep the very good aroma in. But what if we want to keep the coffee fresh even longer? What do we do then? So the obvious thing with chemical reactions is we have to cool down our material. So cooling anything which has some chemical reaction involved, it will always, nearly always slow down the reaction. Now we did first the experiment how freezing the coffee bean if it impacts the degassing or not. So we measured the degassing of freshly roasted and freshly ground coffee, this curve here. Then we froze the same coffee beans for 1 week. After 1 week, we took them out, we ground them. We got exactly the same result. And then we left these beans also 2 weeks in. We took them out after 2 weeks, ground them, and was again the result. So this shows that if we freeze coffee, we don't impact the structure of the bean. It stays the same, because after we take it out, we grind it, we still get the same degassing profile. So that's why I said freezing. It's not really freezing, it's more cooling, because the coffee bean doesn't contain enough water to really produce any crystal structure. If we put it in the freezer, we basically just cool down the coffee to a low temperature. Of course, we wanted to expand this experiment to whole beans to see how, at which time we will start to see any impact on our degassing. So we had, this is a familiar curve for 60 days degassing for the Colombian coffee that was already presented before. This is freshly roasted, and then so we measured it for 60 days, and then the other one was stored in the freezer at -25°C for 70 days, and then it was taken out, and also we measured degassing from these beans after being stored 70 days in the freezer. So we see quite some drop in the amount of CO2 that's released, but still there is a lot of CO2 in. And what we can nicely do here is that if we move this curve up here, we see that it matches exactly the other curve. So what did we do? We stored it for 70 days, but effectively it's like it was stored 2 days at the same conditions as the whole beans that were degassed fresh after roasting, which were at a bit higher temperature, 35 degrees. So what we can say is that 2 days at 35°C was equivalent to 70 days at -25°C. So that's a 70°C difference, and we decreased the degassing rate by 35 times. So there's a nice equation for chemical reactions called the Arrhenius equation, with which we can recalculate how much our rate of degassing increases every 10°C of the temperature difference. And for this case, we get 1.8 times of increase. So we then can say, okay, how much is then, if we compare coffee stored at room temperature to coffee stored at in a domestic freezer, which is -18, so ours was a bit lower, and we can calculate this by the Arrhenius equation, and we say 12.5 times. We decrease the rate of degassing when we have the coffee stored in the freezer. So what does this mean practically? So practically this means that if we say our coffee is good when it's old, when it's from the roasting for 1 to 4 weeks. Let's say that's the optimum period. So if we store the same coffee in the freezer immediately after roasting, we can extend this 1 to 4 weeks period to 3 months to up to a year. So a coffee that was stored in the freezer 1 year will have same amount of CO2 in as a coffee that was stored for 4 weeks at room temperature. Question? Yes.
Have you looked at what happened when you take that coffee out of the freezer and actually grind it compared to the fresh one?
No, not this one. We did the one with it was 1 week and 2 weeks, and we didn't see any difference. But with this one, we didn't test it.
Could it not be that even if in a freezer, when you take it out and actually grind it, you will lose everything anyway?
No, this won't happen because freezing won't impact the structure of the bean.
So you will start the experiment now, right? In 1 year, you will tell us the answer.
Yeah, we will.
Yeah?
It's already ongoing. We just have to wait 1 more year.
We have another question. Oh, sorry.
Yeah, that's okay.
When you stored the beans in the freezer, how were they stored there and packaged? And was it just as per? Were they in the bag and was it sealed and so on?
Yeah, they were stored in a regular bag with a valve. So the aluminum laminated plastic bag with a one-way valve.
Isn't there a cold extraction when you defreeze them, because there is cold water on the beans?
Yes, that's a very important point. So when you defreeze the beans, you should never open the bag until it's completely equilibrated with the room temperature. So my impression is that any difference in extraction or taste for coffee that was frozen and then unfrozen would come from the fact that you opened the bag before it was equilibrated to room temperature, and then you had some condensation on the beans, which changed something for sure on the surface of the bean, because it came in touch with water. But if you really first let the bag equilibrate to room temperature, and I'm saying this should be for maybe a 250 gram bag, should be at least 2 hours. This shouldn't have an impact on the coffee then.
Okay. Did you check also after the freezing how the aromatic compounds left from the coffee, or it's not left, or it stay the same, or you just measured just CO2?
We didn't check the aromatic compounds for this specific thing, but we know that they are stable. We checked in other experiments, the aromatics stay the same. Because they are released at a much slower rate than CO2, the impact of freezing will be less on the aromatics.
Wait. So eager.
Okay, a quick.
This is the last question. Last question.
Okay, a quick question about the carbon monoxide. On lighter roasted coffees, is there less carbon monoxide because of the pyrolytic reactions that you were talking about?
On which kind of coffees? On
a lighter roasted coffee.
Yes, this could be well the case. Yes, unfortunately, we don't have the data to show this. I just took the data from the literature, but there is not really data available on this. I'm sure the big companies, they did the studies, they know what is happening, but unfortunately I can't get the data from them. So there's still a few things. We have a minute or two to show. So I was I was already talking about the extraction, how it impacts, and I made a nice video here which shows extraction with same coffee at 4 different ages from roasting. So we have a fresh roast, we have a coffee that was 10 days old, 2 months, and 1 year. So all will stored in bags for this amount of time. And the extraction was set so that we had the same pressure profile, and the grind size was adjusted so that we had the same brew ratio in the end. As you can see here, or maybe not, that is, it's not very well seen on the projector, but the crema amount on the fresh roast is way larger than on the 10 days, and 2 months and 1 year produces nearly no crema, and also the thickness of the flow going out from the spout, it's like really thick for the fresh roast because it has so much air between the brew, it's suspended in the brew, but then 1 year it's just like water flowing out. I did a bit nicer picture here. Yeah, here it's better seen. You know, this is the last frame. So immediately after the extraction, you can clearly see the amount of crema in producing fresh roast is by far the largest. Here it's already probably acceptable. It's not too much. 2 months it's getting thinner, and 1 year it's like nearly no crema. But that's a good question: is why 1 year old coffee still has crema, even though we lost all the CO2 by degassing. So the CO2 trapped in the beans, it's not the only source of CO2 during brewing. So we can have dissolved CO2 in brewing water if we use the decarbonizer for softening our water. The decarbonizer produces CO2 as a byproduct of the softening, so it can be dissolved in the water and it's released upon the pressure decrease when the water is flowing out from the espresso, so out of the puck. We can have also formation of CO2 by hydrogen carbonate in water by neutralization with coffee acids. So it's a reaction with bicarbonate in water with coffee acids. This produces CO2. So there's a few sources of CO2 that still can make some crema in a very old flat coffee. And if we look how the just a minute, that's the last one. So just a word about how degassing then impacts our extraction. I said earlier, for previous experiments, I adjusted the grind size so that I got the same brew ratios. So I had to adjust the fresh coffee to a grind size of 1.45. It was the same for the 60 days old coffee, and the 10 days old coffee was a bit coarser. And I got the same, this is the beverage mass over time. I got the same profiles, but if I use the same grind size, I got to a result where fresh coffee was flowing really fast through the espresso. 10 days coffee produced a very nice resistance for a very good brew, and then the 2 months old coffee was again flowing much faster. So this is this sounds a bit weird, but we repeated this thing and it was reproducible. So we still need to investigate a bit more why this happened. So since we don't have time, I'll skip the conclusions. And I'm sure there's enough time when you can ask me questions now or later, or send me an email, find me on social media. There's a lot of options how you can contact me.
Well, thank you, Samo. Thank you. Right. Okay.